that's the extremely high reflective index meta material. So particularly, I'm going to use the soft matter rather than conventional lithography approach for achieving this optical metamaterial. Okay, so to start, let me introduce what's the soft matter, because many of you in here might not so familiar with the soft matter, because many of the meta optics still depending on the conventional lithography method rather than soft matter based self-assembly. So soft matter is the material which could be reconfigurable and adaptable according to the external stimuli, like the external mechanical force, heat, and so on. So soft matter is really soft. So it has quite a wide range of material palette as indicated here. So for example, colloid, polymer, DNA, and fluid. So today I will more focus on the colloid rather than otherwise. It can act as a good material palette for achieving unnaturally high reflective index optical metamaterial. So colloid is particle, nanoparticle, which can be well dispersed in the fluid like the liquid and gas. So let me introduce some representative example of colloid. So what you can see here is that individual colloid are well dispersed in fluid and move freely. And so what I want to emphasize at the moment is that its individual colloidal particle can act as a quite good meta atom. So these individual colloidal particle can be assembled by themselves without any kind of the human intervention. So we call it self-assembly process. So individual particle, what you can see here is that individual particle are assembled into the specific super lattice. So let me introduce my favorite. That's published by Stefano Sancanagro at NYU last year. And what you can see here is the differently sized particle are assembled into superstructure, right? Beautiful superstructure with complex lattice geometry. The other daunting feature of this method is that you can bring each individual colloidal particle into super lattice with quite small nanogap, like the 1 nanometer and 2 nanometer. Furthermore, this is quite a wide-scale process and quite cost-effective. Anyone in here can do this method. So I believe this colloidal-based self-assembly can provide good practical platform for achieving optical metamaterial by taking advantage of the several by taking advantage listed in this page. So first, this colloidal particle larger than the natural atom and molecule. What that means is that their electromagnetic response could be much higher than that of the natural atom or molecule, but they still smaller than the wavelength of interest. So what that means is that it can act as a meta atom in terms of effective medium theory. Furthermore, the accessory material element is quite wide, including metal, ceramic, oxide, also polymer. These kind of wide range of material elements are available for the colloidal particle. Also, as I mentioned just now, these colloidal particle can be bring into the superlattice with a few nanometer gap. So really, a nanometer or even a molecular scale resolution can be achieved in a relatively versatile way. So a synthesized colloidal particle, let them in for a while. That's enough to have this such self-assembled colloidal superlattice. Also, we don't need to depend on the lithography method anymore. So cost-effective and wide-scale processing also possible. What that means is that everybody in here could do that without any kind of infrastructure. So I strongly believe that this daunting feature can further democratize the meta optics. And also, as we saw just now, is really 3D and also 2D superstructure can be assessed with the ever-increasing structure complexity. So structural complexity is quite important because it can expand the accessible range of line matter interaction. So In general, I believe that the accessible range of the line matter interaction tend to be proportional to two things: the structural complexity in composition and complexity in the morphology or structure. So we already have quite wide range of composition ranging from the metal, oxide, and polymer. However, accessible structural complexity or morphological complexity is highly limited. If we focus only on the lithography, right? Because lithography basically compatible with two-dimensional process. Also, even with the state of art like the EUV, it still would be difficult to approach to a few nanometer or 10 nanometer scale resolution. So I would like to close this gap by using the soft metal optics. What I mean by soft metal optics is using soft metal rather than hard material lithography for achieving optical metamaterial. So among various line matter interactions, I would like to focus on the refractive index today, because the increasing refractive index can act as a holy grail for various optoelectronics applications. So as you in here might know, the reflective index tend to be proportional to the here polarization. So polarization can act as a determinant for reflective index. So so the challenge become quite simple. So we have to increase the polarization as possible toward maximizing accessible reflective index. Okay, so from this point of view, I'd like to introduce the metallic nanoparticle or metallic colloid as an optical meta-atom. It's long been known that the metallic nanoparticle or metallic colloid can exhibit this kind of localized surface plasmon resonance. At the resonance frequency, accessible polarizability, electric dipole polarizability can be peaked unnaturally. This strength could be much higher than that of natural atom and molecule. So just by dispersing this kind of the gold metallic nanoparticle into medium here, like the water, we can effectively increase the reflective index of overall medium. Okay, so as you already know, the reflective index of water is about 1.33. But just by just by dispersing the gold nanoparticle, that's enough to effectively increase the reflective index as indicated here. Because the metallic nanoparticle has much higher electron density or an optical conductivity. So these two things synergistically increase the accessible polarization, and then we can achieve the enhanced reflective index. Yeah, so quite good, quite simple. This is quite versatile way. Anyone in here can purchase the gold nanoparticle from the company and dispersing this one into any fluid, you can achieve effective increase in the reflective index. But I want to go further. So in order to further increase the polarization, I'd like to use the capacitive coupling throughout the metallic nanogap. So here is the golden spherical golden particle, and we can just simply put them in onto the gold mirror, flat mirror. And this particle and mirror can be separated by the quite thin dielectric layer with 1 nanometer and 2 nanometer thickness. So when they are illuminated with the light, this particle can form the electric dipole as indicated here. And this induced dipole also translated into the mirror as imaginary. So this we can expect the two electric dipole here and there. And this induced electric dipole going to be coupled through the capacitance. So polarization can be further increased as evidenced by strongly confined light at the gap. Okay. So same thing can be happen with the dimer. It's the golden nano cluster is dimer. And between the dimer, we can form the nanogap. this point-like space, and we can squeeze the light into such a point-like space through the capacitive coupling of two induced dipole. So then it's time to imagine what's going to happen when we array such a meta atom over the large area, much like this one, much like this one. So long time ago, several guys indicated here expect that when we increase the volume fraction of this conductive sphere, we can effectively and unnaturally increase the accessible permittivity. Okay, here F indicates the volume fraction of the conductive sphere. So higher fraction of a conductive sphere means that the spacing between the conductive sphere get decreased. So in turns, which in turns make it more strongly coupled. So accessible permittivity can be unnaturally increased for relatively high volume fraction of a conducting sphere. This is quite good because just by putting the conductive sphere into the specific volume, that's enough to unnaturally increase the effective permittivity and the resultant reflective index, because the accessible polarization can be dramatically increased because they're going to be further addressed by capacitive coupling. Okay, so this philosophy can be translated into the optical region. So let's say we're gonna have the silver nanoparticle. It's shaped with the cube, right? Cube. So let's say it has the 15 nanometer size. And let's see what's going to happen when the gap of this metal nanoparticle superlattice is decreased from 8 nanometer to 1 nanometer. So just by decreasing the gap, what you can see here is the effective permittivity can be dramatically increased, particularly at the resonant region. Here is the electric dipole resonance. Okay, so you need to recognize the 10 to the 2. So what that means that here is about 450 of the effective electric permittivity. It's much more higher than that of the naturally accessible region. Okay, so capacitive coupling can be further evidenced by this slide. So what you can see here is that by decreasing gap, more light can be squeezed between the gap. Okay. So the other evidence of the capacitance dependency of this kind of natural behavior is that by changing the shape of each method, because the capacitance depending on the interfacial area between the conductive units, so from sphere to cube, here sphere, octahedral, and cube. What you can see here is the interfacial area become more increased. So which in turn, what we expect is that the accessible electric dipole resonance can be further enhanced. Yeah, so it's quite good. So what popped up in your head could be like this. So okay, so unnatural increase in reflective index is quite good, but this resonant behavior should suffer from the significant optical loss. According to the KK relation. Yeah, we are quite familiar with the Kramer-Kroll relation, right? So actually, so at the resonant region, significant optical loss is inevitable, but at the off resonant region, so accessible reflective index can be still higher than that of naturally occurring region. While simultaneously, we can expect a significantly negligible optical loss. So as a result, we can still expect the high figure of merit, which defined by real reflective index over the imaginary counterpart. Okay. Also, actually, this guy is quite useful for optoelectronics, such as solar cells. So let's say we're gonna have the perovskite, and we can put such a high reflective index metamaterial into there. So what you can see here is that reflective index of perovskite actually increased. As a result, the absorption can be increased, accessible current also can be increased. Eventually, we can enhance the power conversion efficiency as well. Okay, so it's quite good. So far we have discussed about the theoretical consideration, and it's time to assemble the design the structure. So our group can synthesize the golden nanoparticle with well-defined shape and relatively high uniformity as indicated here. So our unprecedented uniformity of our synthesized golden particle also evidenced by high uniform dark field scattering. Okay. Yeah, and then it's time to assemble them. So we are going to use entropy packing. So when the particle is confined at the two-dimensional area, and if you can put some thermal energy, they're going to be crystallized due to the entropy effect. So same thing can be happen at the nanoscale. So let's say we're gonna have the nanocube confined at the two-dimensional areas, and just by increasing the volume fraction of the cube, what you can see here is that the particle going to be crystallized and packed. Where so this simulation result experimentally realized well. So about 50 or 80 gold nanocube are well packed and assembled over the large area, and actually this material exhibit unnaturally high reflective index at the resonant region. That's actually about the NIR. And also off-resonant region that correspond to the mid-IR region. These materials still show the higher reflective index compared with the naturally accessible upper limit of, for example, silicon and germanium. Okay, so to conclude, so far I have introduced how effective and how useful of this self-assembly of soft matter, particularly for achieving unnaturally high reflective index at the optical region. And also, lastly, I'd like to thank my students, including Dr. Jia Kaur, Hwang Jin Kim, and Jaewon Lee. They made a lot of contribution to make it happen. And also, thanks again for section organization and audience in here. So I'm more than happy to have answer if you might have. Thank you.
Thank you very much. Wonderful talk, very important that I see here. Let me see, there's one. Okay, all right, there's the one question. The polarization will be shape dependent on nanoparticle. This is not
Yes,
yours. Yeah.
Yes. Let me share again. Yes, as indicated here, this capacitive coupling between the meta atom should depending on the shape, because more high, large interface area between the conducting unit ensure more stronger capacitive coupling between them. Yeah, so capacitance tend to depending on the shape of interface or interface. Yeah, actually. So this the cube, as you can see here, cube can have a higher interface area compared with that of sphere and octahedron. That's the main reason why they can exhibit more higher reflective, higher permittivity and reflective index as indicated here. Or more stronger capacitive coupling can be further evidenced by more redshift electric dipole resonant peak as well.
So that answers the question, or anybody else? Then okay, I have one case. This is wonderful work, and then I remember people tried the capacitive coupling not in optical wavelengths, but like a terahertz, because that's easier to fabricate, and they report the wonderful, very high reflective index. But yours is, I mean, the more visible near IR. I just wonder, I mean, you showed like a 1 micron is very high, and if we come back to the shorter wavelengths, it just goes down. So what determines the resonance peak? If you can move it toward the more visible wavelengths, that will be really, really useful. What determines that?
Several variables can define the working wavelengths, as for example, size of the individual particle or gap between the individual particles. So for a large particle, can push the working wavelength to more redshifted region, while for a shorter gap, can push the working wavelength to more redshifted region.
Okay, all right. Thank you.
Also, this element of plasmonic particle also can define the working wavelengths as well.
Okay, there was the one more, I think what it is answered, or what shape maximizes the shape? I mean, it's a little bit typo here. So another question was, I think you answered that. So let's move on to let's
Okay.
conclude your talk. Thank you very much. Let's move on to Dr.